way to conceive of a community code being different is that you have engaged more than just your group, right, in the development of that code or the use of that code. So often community codes have a mechanism for diverse development. So you've got people, geographically diverse committing to that code, preferably people who are also working on different scientific problems, not preferably, but often working on different scientific problems. That impacts things, right? Because you're maybe not always talking the exact same language. You don't always have the exact same mission in mind. But it's that concept, right, that you have joint development of a project rather than just open sourcing it. It's not just that somebody can download it, it's that somebody might download it and then be able to even offer up changes and advancements to that. And it's that particular aspect, right, the offer up changes, offer up new features in a code that's really particularly challenging in the scientific community. My side note will be, right, that most people come from a world right there where they have control over the code that they're developing. It is their science, right? And you want to control that because this is your life, right? This is the thing you're doing, and you want to be able to understand every aspect to it. And so when that goes into a community model, that gets weirder. And that has often been more challenging for scientists to adopt. Some communities are really good about it. And in part, sometimes that's motivated by their funding choices, right? Their funding choices have said, converge, we will not support 10 codes to do this problem. I want, the funding agencies want 2 or something like that. But sometimes it's also really the recognition that there's incredible complexity, and it's a lot easier to get to your science, right, if there's some joint efforts to get the code done. That's sort of the quick, does that clarify for you sort of what I mean when I'm talking about the difference? Great. Many of the things I'll talk about also impact open source projects, right? Because in the end, the software engineering process should impact you if you are writing code on your laptop. You should care about a software engineering process. It does not matter if you are alone and you are doing it on your own, because I guarantee you, you're busy, you're doing a lot of things, and in a year, you might go back to your code and not remember what you did. So it will happen. Even if you're young and with a really good memory, and every day you age, it's going to get even harder to remember what you did that year and why the code looks that way, even if you thought it was obvious at the time. So the software engineering process really relates to you as the individual developer all the way up to large teams. It just becomes even more crucial as you're talking about growing complexity of codes, teams, and hardware. And I've been talking around this, but I realized that I started talking about software engineering in this slide set, and I didn't define it. Now, most people raise their hands. This is great that they have seen software engineering somehow, that they've considered it, and they've thought about how it might impact their work. But fundamentally, all we are talking about software engineering is a process, right? Fundamentally, we're talking about a way that you have a plan, preferably documented that plan, that you can share with somebody, right, about how you're developing this code, how you're developing whatever project you have. And what's also interesting, though, about software engineering in the science community is that there's sort of a transition from like implementation, right, where you have the architecture, right, and how you name routines, for example, all the way through to process, really the scientific process, right, of how you track what simulations you ran. And this also is something that will be talked about in the next couple of days. How you track what simulations you ran and what versions of the code that was, and how you have reproducibility. So it transitions from not just implementation, but also really that process of your day-to-day workflow. The other component to realize for engineering, and this is also why it's very heartening to see people raise their hands. I tell you that 10 years ago, people might have raised their hands that, yes, they've heard of software engineering and they've considered it. The other question is how many people would think that they're implementing decent software engineering practices? And I'll ask that. How many people think they're sort of doing it today? That's awesome. There's a few people. And I'll say, it's okay not to raise your hand, right? One of the things that's beneficial about not raising your hand is at least you're thinking critically that maybe I don't have the right solution, or maybe I'm not doing everything perfectly. Just remember, document it, right? It's just a process that you're capturing. But the other component to this is that the scientific community, for the most part, is transitioning to a different way of operating in HPC, where software engineering is really becoming not just important and valuable, for your scientific process, but also really crucial for your scientific process because you won't be able to get funding to write your code. If I had said this 3 years ago, I think people would have started throwing tomatoes at me, because they would have been throwing tomatoes at me saying, well, give me funding to write my code, and then we'll talk about a software engineering process. It hasn't been the best set of 10 years, right, for funding for codes. But there's a lot of funding that is on the table right now for code development. And a lot of real transition. It has taken a while, right, for people to recognize that if they want, especially at the extreme scale, scientific code to be ready at the extreme scale, you need to fund that development and have it be decent professional scientific code development. And most of them already have some request for documenting your software engineering process, and the ones that don't are considering it. So that's the other reason to think about it, and think about it hard. From a day-to-day perspective, I'm going to tell you something that you probably already know, right? Which is that scientific codes are complex. It is not as simple, right, as figuring out your physical model and throwing them on the machine and you're done, right? It would be lovely, and it is not the case. So when you're talking about a scientific code, you absolutely are driven by whatever your physical model might be for the scientific problem you have, right? But you have to incorporate a lot of applied mathematics, right? Not just for representing your physical model, but you need to incorporate a lot of applied mathematics for performance. And then integrating computer science to making sure that that code is working effectively and that you're using the machine effectively. Challenges with I/O. This is the single most non-portable problem we've had over the course of the past 15 years, and it's still not totally solved. Data, how you do data management, right? If you're dropping or bringing in data, a lot of data, or moving out a lot of data, how do you manage that? How do you tag it? How do you understand it? How do you verify and validate your data? Right? How do you verify that your code is doing what you think it should do, right? You think your code is saying that 2 is a result of 1 + 1, so prove it, right? You need to do that. You need to verify it. And you also need to validate it, right? You also need to validate that it is consistent with the science that you want to predict, right? So all of these things go in and more, right? It's a complex process and it never ends, right? You don't figure out your physical model and walk away and be done, because you figure out a physical model that you use, you do all this stuff, you do a simulation, and 2 years later, your scientific understanding is better, right? You might have new questions you want to ask and you need to incorporate new physics. So it's this continuous iterative process, and they're complex. And I'm going to repeat this later in a different way. It is unlikely that you are going to have expertise in all of these areas. You're going to have to bring people in to help you. And when you have a code that's parsable, that's understandable, that is documented, that is tested, you can have a much faster and more effective collaboration with people who come in to help, right? So some component of this is bringing in a long-term collaboration with joint funding. Sometimes this is going to a computing facility, right, and saying, my I/O is terrible, or I need really better performance because I can't get my science done. If you can bring a well-engineered code, that collaboration goes a lot faster. I can tell you this from a lot of experience, right? I've been doing this actually for a long time, over 20 years. And when somebody can give you, for example, a modularized problem, right? Like, here's my I/O module, right, that I need to worry about, and it's performing terribly, let's do tests on your system. That's a lot faster and more effective than when you have to run the whole simulation and sort of pull out I/O integrated within all kinds of different parts of the code, right? So this is an example of modularization really helping. But the other component to this, right, is that not only are you unlikely to be experts in all of these things, when you want to talk about the extreme scale, if you want to talk about exascale, if you want to talk about leadership computing facilities, yeah, we're kind of breaking everything while we do it, right? We're deploying machines that are on the bleeding edge. We're deploying machines with brand new technology and new implementations. We're doing things that you might be able to get on your laptop, but maybe not immediately, not for another year or two, right? So you need some flexibility in your development, because if you want to use these machines, you're often coming onto machines that are substantially different than what you have anywhere else. And this leads to something else I've alluded to, which is a really common thing, and I have done this. Anshu has done this. I'm guessing that many people in this room have done this, because it's incredibly pervasive in scientific computing, which is the heroic programming model, if you will, right? And that's where you have an individual, right? A smart person who really knows what they're doing, who goes off and really throws 6 months to the wind, and it just generates tons and tons of code, right? They go about this huge process of solving the technical challenge of the code writing. And this is pervasive in science, I would say, for a handful of reasons. Most often, it is that science does not come in with a code team of 6 professional code writers ready to go and tackle problems. It comes in with funding for a grad student and a postdoc. And you have to get a problem done. And if you're a grad student or even a postdoc, right, you've got your papers or your degree reliant on you getting it done. And so you're really motivated to get that done, right? And I completely understand that, right? Our environment supports the heroic programming model in many respects. But in the end, it is a manifestation of a problem, right? And the problem might be that there is not enough funding, right, to properly develop the code you're looking at. But it also really often reflects that there's challenges in how you're planning out the code development, right? Or there are schedule pressures for it. So as I said, science teams most often resemble this heroic programming model. And the only thing I ask, right, there's good reasons why it's reflected, but many don't see any challenges with this approach. So I will ask the question, right, and I was funny, because I was asked by folks earlier whether I was gonna actually be more interactive with the group, and so I'm throwing that to the wind. Can anybody describe what they think would be challenging or a problem with the heroic programming model approach? Programming model being, of course, a poor choice to use right now. Why is that a problem for science? One of the things is that you won't finish everything, right? Like you'll be on a process to sort of work on a new physics model, or you're on your process to fix the I/O, and you get distracted or something pulls you off, and so you end up with an incompleted process. Even if you finish the code, perhaps you never finish documenting it, right? Or you never finish writing that unit test to make sure that actually does what you need it to do. Those last two, I think, are the most common ones that fall by the wayside, right? You've got it, it gives you something, right? Let's move on and we get to the next thing that's urgent. The heroic programming approach. That means you've got 1 or 2 people who've got their heads down and they're beating your code into submission, right? They're doing everything. It's hard to bring people in and get them incorporated into that often, right? It's hard, right? If you've been focused uniquely on doing something for 12 months and you want to get somebody up to speed, that can look like just a drag on your time, right, of going forward. But it also means that you probably are giving up those unit tests and that documentation and all of these things that make it easier for somebody to look at your code and figure out what you're doing, right? That if you can write a scientific application that works at extreme scale, that works on exascale, that works on petascale today, I will tell you, you are a rare commodity. And if you burn out, this is a problem. This is certainly a problem for me, right? It is a problem for the community. And it means that if you are a PI, right, running a group, and you've got somebody who's doing that, you've got a lot of very important information in that person's head, and you don't want that person to go away. And I can tell you when they do, it's hard, right? And it really is true. While I recognize, and I have some memory, at least that like at 25, I had much more energy and ability to go like crazy for 6 months, right? There is a limit, and there's a limit for everybody. Okay. And it also means that even on the burnout side, there's burnout on the other end. And what I mean is that if you're given 100,000 lines of code and said, hey, somebody wrote this 2 years ago and we have no idea what this module is doing, I tell you that can also lead to a different kind of burnout pretty quickly. Any other ideas? And I'll move on to the next. Okay. These are really excellent points, right, about why heroic programming is a challenge. And another illustration really about why it's not only that you lose people and you don't get everything done, I would argue that it is also almost impossible to consider large-scale computing over the course of the next 10 or 15 years with this model. And the reason is heroic programming is also inherently focused on that 1 or 2 hero model, right? You have that 1 person or 2 people who kind of have everything about your code in their head. Or perhaps you are one of those people too, right? The problem is that requires a lot of expertise in their head. That requires a lot of time cycles, right? And do they really have the ability to be an expert in everything you need to consider? And this goes back to something I said earlier, right? One of the challenges with heroic programming is that first, right, you start right out that you have a code and you do some simulations on it. If everything goes as I expect you are planning it to go, the point is for better scientific understanding of your particular problem, right? You will glean from your work some important new thing that you want to study. Maybe other researchers are driving you, right, to consider new features of your scientific code. And you will have a need for a more complex piece of software. Most of the time, even if you decided, right, that, oh, I can model this particular complex thing, right, that was bringing in huge length scales, that's because you're also doing something else, like bringing in bigger length scales on some other component, right, of problem that you're trying to solve. Very rarely do we see the complexity of the physics. I don't think I've ever seen it, but I'm not saying it's never happened. I've just never seen it. The complexity of the science that people are trying to work on decrease. And that means the complexity of the code is increasing. The more types of physics, that you want to bring in, and I'm saying physics here, and please, this is just my own problem of lingo and training. I mean this in a larger term, whatever your domain science problem is. But you have a more complex software. And as I was mentioning before, right, scientific code has this wide variety of things in it. It is not just your physical model and your MPI implementation, right? It is your math model, but it is also the numerics, it's the verification, it's the performance, it's the implementation, it's the data structures. And while it is useful in that process that the person who understands the math model probably understands a decent amount about the numerics, and they're talking to somebody who's an expert in numerics, it's rare that somebody covers all of these aspects of the code, can really talk to all of them effectively. Even on some of our most effective sort of hero codes that we use at the ALCF, those codes still come to us or go to other people and say, this is interesting, right? But we need a new way of solving this problem. The physical model isn't exactly what we need. So they have to go externally, right, to bring in that collaborator to improve what they're doing in their code. Or they want to get performance, right? They really need to get every last possible theoretical flop out of the machine, because that's how computationally intensive their problem is. And so they come to us and say, how can we do this? How can we re-architect the code? So even these really, I would say, very advanced code teams, right, that we collaborate with, still have to go out, right, are still trying to pull people in. Without an engineering process, communication gets really challenging. And I think Anshu very recently got this direct question on it was a webinar that we were doing, right, which was, are we past the days where a single PI, right, can write their code and get that implemented and run on an exascale machine? And I agree with her answer, which is that no, we really are no longer in that place, right? You really do need multiple people working with you. The level of complexity of these problems is so large that we don't see it being successful today, and we see it be even harder as we go forward with a lot of the things that you've already heard, like this past week, right? With the changes in hardware architecture, the evolution in the software stack, and with the incredible rate of complexity of the science, right? The maturation of a lot of the science that people are trying to do, and the evolution of it. These things make it a very complex problem. Now you might be saying, I've just painted this picture of like, oh, it's just really, really hard. But again, all this is trying to point out is that it is hard. You should expect it to be somewhat hard. And there are tools you can use to make it at least somewhat easier, right? And this is where software engineering really can come in and help you move forward. So as I was mentioning, right, that with extreme scale science, I'm hammering the point a little bit home that you're not just dealing with increased complexity of science and an increased complexity of code. You're dealing with also an environment that is changing very rapidly. So the leadership computing facilities, right? So what we really are the largest open source systems that we deploy in the country, we have a pretty regular cadence of those being replaced, right? For most people who have sort of the historical model of code development, right, which is that it is one or two people, the 5-year time frame, approximately 5-year time frame, where one of these big machines lives is about the time frame that they're able to, if they were just doing it on their own, get their code really used to and doing well on the machine, right? If you are one person trying to use, especially this was true like 2 years ago, one person trying to use a 10 petaflop machine really effectively, maybe not take 5 full years, right? But it takes more than a couple months. And so having a code, right, that is able to be adaptable, that you're able to move quickly, you're able to modularize, right, you're able to bring in collaborators to help accelerate your work is really crucial. And this is something that sometimes people don't think about, right? Because it is different than your laptop, right? Using an extreme scale machine, using an exascale, using even a petaflop machine today, it is not, or a large petaflop machine today, it is different than a cluster. And so you have to make special considerations when you make that jump. The other component to this, right, is remember that we don't even know completely where hardware is going over the course of the next 15 years. I will say, having watched it, right, 10 years ago, there was certainly a lot of consternation about what we would do with petascale computing. 10 years ago, thinking about how we will get to a petaflop, maybe it's 15 years ago now, but figuring out what we would do. But for the most, and people thinking about really dramatic things that we would do, but for the most part, we sort of walked along with the exact same rhythm of what we'd been doing, which is that you had many core, sort of early many core machines running MPI, and you could sort of march ahead, and you would have to think about performance. It wasn't that you got performance for free in all of these cases, but for the most part, it was the same process. It is not. It is possible that we're talking about big architectural changes, not just one, right, but one per generation, right? That you're talking about something big that changes every time you take a step. We know in part this is happening, right? Because we see, right, what we're going to put on the floor in a year. We see what we're going to, and what we're likely to put on the floor in 5 years beyond that. We have a very good understanding of it, and what we're seeing is a lot more heterogeneity, and not just on accelerated machines, right? Not just a GPU-based machine. Heterogeneity here isn't necessarily just, I'm going to choose to keep with many core, and it will be sort of kind of similar. We see a lot of divergence and a lot new hardware coming on the floor, to the point where I find it kind of exciting, because it has been 20 years of sort of, MPI-like work, right, and scalability sort of coming along. It is both exciting and terrifying, right, from a scientific applications perspective. I think the abilities that we'll have are astounding, but we need scientific code to be able to come up and meet that. Okay, so some of the other reasons, I've sort of moved away from talking as much about software engineering, but I'll say one of the other reasons to really consider this is that consider software engineering and how you can incorporate this to make your development processes easier, to make incorporating people into your process easier, is that the accumulated cost actually can be pretty substantial if you don't. I'm very sensitive to the fact, right, that we're not talking about people getting millions and millions of dollars for every grant for projects that they want to do. But it is worth considering, right, the long-term science goals that you have with the code that you're developing. It might be that true, right, that in the course of this year, it's a lot more effective to just get stuff done and leave principles of software engineering behind. But in terms of cost savings, you might actually end up paying a lot more for that over the course of 2 or 3 or 5 years. And this has been shown over and over again, right, that where a little bit of thought early on about how you design a code, about how you think about the data structures, about documenting the code can save a lot of time. I sort of feel like this one is almost obvious, but it's worth pointing out that not documenting a code can translate to 5 years down the line, somebody having to spend 6 or 8 months of their time trying to unwind what's going on there. And not just, how the code is architected, but really actually the physics of what's going on in there. The physics might be lost if the person who wrote it has disengaged and moved on. That needs to be captured. And so if you have to spend 8 months unwinding what was going on there to figure out if it actually can do the thing you want it to do or if it's doing what you expect it to do, think about that loss. It's a pretty substantial loss in time. So the other component to this really, there's specific points here, but is to consider that this issue that it's not just that you might not be doing what you expect it to do, but it might become completely unusable over time. This could be because of changes in hardware. It could be because you've moved forward in the development of a new physical model, not realizing that you wouldn't be able to use these other components of your code because you didn't know of the requirements that they had, or of the performance impact, right, that using these other components of your physical model might have in where you're going. All of these things come together in sort of one term that we often use. The term is technical debt, and it's really the consequences of the choices you make today. So technical debt you can think about, right, is you make a choice today about how you're developing your code. They don't all have to be perfect choices, right? But you've made the choice of how you're doing it, and at some point you have to address both the good things and the bad things, or the consequences of both the good things and the bad things that you have decided. And I think this is a great description of it, because one of the things it points out is that debt is not bad necessarily, right? Per se, that is not bad. There are times where you might make a strategic decision that I have to do it this way right now for funding reasons, for people reasons, right? I just can't find the people to do it or whatever. But you need to understand it and you need to manage it, right? You need to have that you have to be aware of it, right? And perhaps that just needs to be, loudly documented. We did this in a really haphazard way, right? Be aware of the following assumptions that we've made or something, right? You have to manage the choices. And to some degree, you could think about that really being the fundamental to software engineering. You need to make a decision about a process. You need to commit to that process, and you need to get people to buy into that process, right? You need to make the people who are working with you commit to that process, even if it's simple. And you need to think about the long-term consequences of it. Collaboration is incredibly difficult to do if you don't have that process. And this is, as I've said, this can be collaborations in terms of developing new long-term funding opportunities with people, or going to experts and sort of saying, hey, help me with my performance, help me with I/O, help me with my data structures, help me with what have you, right? It gets trickier because there's an interesting overlap, right, between wanting to make the development, the productivity, right, of the developer really easy. So using languages, using things, right, that will make your development process easier. And then also understanding, unfortunately, that as of today anyway, and as of probably still true over the course of the next few years, the environment on an exascale machine might not support all of your development options. And so this is the other component to think about this. And it's unfortunate but true, right? We often get questions about, why don't you support this programming language? Why don't you support this model or this library or this framework, right, on a particularly large machine? And often the reason comes down to this issue that I'm talking about, right, where we're putting down bleeding edge machines. And the software takes time to catch up, right? Because the software stack, whether it's a programming language or a library or even the operating system, right, is also trying to run on bleeding edge hardware. And so this is an important component to think about in your software engineering, and why there's other aspects of how I wrap this in. Software engineering for scientific codes is not the same as looking at software engineering practices for industry and just applying them. It is not the same. And you have to consider these differences, that there are ways that the machine, because of the machine itself and the software stack that's being deployed, that you will not have the same environment as you do on a cluster, or that you have on a cloud, or that you have on your laptop. And on top of that, right, we also live in sort of the scientific community where funding is also very, very different, right? So all of these and more things combined, that the process will be different. So I would encourage you not to just necessarily look at the best practices for a particular company and try to pull those in without considerable thought. There might be really good reasons to pull them in, and you just have to put the thought through them and understand the consequences of them. If you want to develop a new high-level programming language, understand where that language might be available, right? Understand what the challenges will be with it. Consider if you can own it, right? Like if you want to program in a high-level programming language, can you bring that programming language to a computer, a large-scale machine, and actually deploy it yourself? This is sometimes what people think about. They think about this when they want to do a library, especially large-level framework libraries. A lot of scientific developers will just take that library and sort of take ownership of it and say that if I'm bringing my code to a machine, I'm also bringing this version of the library that I'm using and dependent on. This particular slide is mostly one, it's about a year old, but this data down here, but I'll point it out, right? Because this is often really, really shocking for some people. Maybe not everybody in this room, right? But it's often really surprising to people when we talk about the code distribution on these machines. This is shocking to people within the scientific computing community sometimes. Within HPC, people are like, what? There's that large of a fraction of Fortran codes on your machine, for example, right? People are really surprised by that. This isn't me saying, hey, let's look at what C, C++, and Fortran codes are on the machine and break them down. This is what the codes are written in that are running, say, on the ALCF platform. Well, technically this was last year, but the ratios look about the same. They are not in high-level languages. Now, there's a great question, and there's been a really good conversation, right, over the course of the past year. Why is it only these languages? And will Fortran still be there, right? And why can't we get a higher level language on these machines? And one of the things we are actively trying to do is really encourage, we are trying to push, right, the improvement of the ecosystem on extreme scale machines, on the petascale machines that are deployed today, and the machines will have the next generation of machines and the generations of that. We're trying to improve that ecosystem. But in the end, the reason that we have C, C++, and Fortran on the machines today is these are languages that you can get performance out of, that get reliable performance out of, and that vendors write compilers for. That may sound silly, right? But it's true. And I am not making an argument about what language you want to use. But I point out, right, that if you're thinking about software engineering and you're thinking about your productivity and thinking about perhaps even just what programming language you will use and programming model you will use, these are great questions to ask. But think about where you want that code to go. Because again, thinking about the consequences, depending on your choice, you might not be able to take it everywhere you want to go. What I do tell people when they're really thinking about these things, when they're thinking about not dealing with the code that's been around already for a while, they're thinking about something new, and there are people writing new codes today aggressively, right? Is one of the things I say is that actually if you talk to the people running these machines, talk to the scientists at these facilities, talk to people involved in the community, you will get a good idea about what we will be putting on these machines, right? What we are trying to make available. There's a lot of people who can stand up and say, I will have my product available in 2 years on these machines, right? But unless they're working with the computing facilities, for example, not just the DOE one, this NSF too, everybody, right? Unless they're working with them, those capabilities might not be available. So talk to people about them, please. That's all I'll say, right? About this is think about that. Not everything will be available. And it has a lot more of a gloom and doom type sound to it. I'm not trying to make it sound gloom and doom. I'm trying to make it more sound just about a sort of a collaborative effort, or at least a conversation. Realize that there is sometimes a disconnect between new exciting things that are coming around and what can actually be put on large computing infrastructures. One of the other things I wanted to point out, right, I just wanted you to start thinking about these, and this is sort of switching gears a little bit, is about what kind of code you use and how you interact with it, what your relationship is with it. There are all kinds of different users, right, and types of different computational scientists, right? Some from people who use a code in sort of a black box way, meaning that you are using a code, right? You're using code X, right? And you know what parameters you want to give it and run it, and it gives you an answer, right? And you don't necessarily commit to the code development of it, all the way down to, you are the code development team and the science team working on it all jointly. There is no one of these, right, that is better than the other. And for every one of these, you will have somebody who stand up and will passionately say it is the best of all of these options, right? From you being a black box user to using libraries or not using libraries and developing your code and owning it completely, because that is science, right? You own it completely. There is no one way that is better, right? It is really a function of all kinds of aspects of your particular kind of ecosystem, right? Like the environment that you are in, what science you're trying to get done, and what resources you have, and what is already available and out there. But also understand, in the same vein of understanding the consequences of your choices and the impact of your choices, that depending on whether you choose to be a black box user or a developer but using a lot of libraries, or the complete owner of your code, that where you go and how fast you get there, it changes, right? If you want just to get an answer, right? You need an answer, and you need the answer today or tomorrow, or at least a month from now, all totally reasonable timeframes. You probably need to be a black box user, right? If you don't already have a solution in front of you. And if you decide you're going to write your code, I think it's important to understand that for good scientific process, right, you're going to get to an answer at a much slower rate than if you're a black box user. Similarly, though, if you need to deploy new capabilities, right, understand that if you think, I might need to study this problem, but then start really tweaking it, right, tweaking the physical model and tweaking the amount of physics involved in it, you won't necessarily have that ability with a black box code. Right? Kind of depends on the code. Some codes you might be using that are black box codes are community codes. So you transition from being a black box user to actually a developer. But that will slow you down, right, if you need to make transitions in it. So again, this is all things that I don't think are very complex. You can sort of realize them, but you might not always think about them when you're making the choice of how you want to solve the problem. And I don't say this because I just think it's important for people to think about. We see this. We see people run into these walls, right, where they haven't necessarily considered that maybe the black box code they're using won't scale, right, to the place where they need it to scale to solve the science they're now interested in doing. That does not mean, right, you're all adults, you can all plan. That does not mean you should throw out a path because tomorrow you think, well, maybe though, maybe I need to write my own code because I don't know exactly what the path will be, right? I don't know exactly what I want to do. I think all that's important, right, is not that you have to opt to write your own code because you're not sure. This has been the default scientific path for a very long time, right? I'm not sure, I want to control it, so I will write my own. That's totally reasonable, but not always the right solution. And it might be completely reasonable to be a black box user for a while and then sort of transition, again, if it's a community code, to transition to being a developer. Or to realize that nothing out there does really what I want it to do. And at least you've done sort of the due diligence of proving that nothing out there does. And then maybe you do need to develop a new capability. But just understand that. Just understand, again, the consequences of them. And this is a little bit, I've always loved this slide. This slide is actually quite old now. But it's, again, understanding trade-offs and what you want to think about caring about in your code. In some cases, so what this is supposed to show, and does, but just shows it for slightly a different time frame, is if you want to worry most about correctness or efficiency, how that affects your reliability on your code, or your accuracy, or your robustness, right? So that if you work to increase one, does it decrease the other one? And what I really want you to see out of this, if you really care particularly about the impact of robustness on accuracy, we can talk about that. But that there is an impact, right? If you have finite time, which I'm pretty sure everybody does, and finite funding, which is pretty much not just the only function of having finite time, or the only driver for having finite time, that you do have to also prioritize within what are generally considered really important aspects of your code, right? Which are these aspects of portability and portable performance, and adaptability, right, and modularization. You have to think about within the scope of what you have to work with, within the people and the time, the funding, and the science. What are the most important? But given that, I will say that one of the most important things really is that you need some software engineering. And the other component that we'll talk even more about tomorrow is that you also need to prove that your code is correct, right? That you have verified it, you have validated it. And the process of scientific engineering, or software engineering will help you in that process. It is not meant to be onerous. It is not meant to break you. It is not meant to be another list of requirements, but a way to make the actual development process easier. If you want to be more productive, and you're hearing lots of talk about productivity these days and scientific developer productivity, if you want to be most productive, the first thing you should look at are your engineering practices. And if you're not sure if they're good, you should talk to somebody who you think knows about software engineering and still look at that conversation with a critical eye. But that's what you should do. Don't think about whole big overhauls of anything until you've looked at your process and figured out, okay, let's iterate and improve that process. And then if that process is still not getting me where I need to go, maybe I need to look at something bigger. But look at your process first. And just remember, right, in terms of objectives, we're not trying to sell you on a tool or a code. We're not trying to sell you on a specific process, except to think about your engineering practices, think about what you're doing, think about how you can improve them. That's all we ask you to do. And so how we want to make you have that conversation with yourself and with your group is to give you some new tools, some new ideas, some new people you can go talk to.
So I think software engineering practices are something that most everyone would recognize as an inherent good. But I think there are a lot of people who, as you've illustrated, would think that they just don't have the time or money for it. And so I know there are a lot of people that won't change until there are more external motivations to do so. And so you talked about requiring it as part of funding. And so maybe I was wondering if you could talk more about other kind of sources of external motivation that
Great, yeah, I will say, and I've seen this with other things, that motivation through funding is really the biggest driver. I don't think anybody can argue with that. But one of the other places where we've also seen it is competition, right? If you have a collaborator / competitor, and they're all sort of fall in that category in science, right? Who is moving faster than you because their code is more adaptable and more able to bring in new features and able to use some of the challenging systems we're gonna see in the next 10 years. That's also been a big motivator. Now we've seen this to some degree. We've seen this in other communities where people have really upped their game because they're getting trounced by someone else, but we haven't seen it pervasively. But one of the other challenges is that doesn't work actually in communities where the value of the code doesn't exist, right? So there are some sub-communities where black box use of codes, complete black box use of codes is sort of really completely pervasive. And that is how people work, right? They run their codes, boom, done. And to some degree, right, they often don't see beyond, I'm gonna use my black box code to do this. And it's a lot harder in that community when you don't have people who wanna sort of take that capability and grow it to trigger change, because everybody's sort of doing it to get the fastest result we can. So that's I think, the most difficult community. But otherwise, I think this combination of competition and really in terms of what science you can get done combined with funding is gonna be those two things combined are gonna be the biggest motivator. One other extra thought I'll add to that is that there is an absolute challenge with whether you internally want to get your science done. Like whether you personally decide that you're gonna change the course of what science you want to do, or whether you want to use, for example, some of these new machines coming on. And most of the time when you want to use those new machines, you really might need to be considering wrapping in software engineering practices to get there. And that will impact your ability to get people. So one other aspect I'll say, and I know Anshu has something to add to this, is that I am not joking, codes are going to get more complex and the systems are getting more complex. And if you want to use them, you will need to recruit people and you will need to retain people. And this gets back to this point earlier, that without those engineering practices, you won't be able to get them. Or at least you're gonna get them and they're gonna burn out fast. So you might have to go through 2 or 3 people before you've improved your practices enough that you've got people to stick around. But there's a real personal driver there, right? That you won't be able to keep the people. And what I've also seen, frankly, is that you've got sort of it's not even just like the next generation, but I mean, people coming out of school today, right, who have much more extreme assumptions about what's going to go on their scientific code, and I think they're coming in with some better ideas about practices. Anshu, wanted to add to it?
One way in which this practice has been spreading is that there are new people who come into a group that has a good software engineering practice going, and they realize the value of it, and they refuse to work without it. And so they take that culture with them wherever they go.
So I'm just curious about the opposite situation. So let's take a hypothetical example where you're a person who follows good software engineering practices and you go into a group that doesn't. What would be a good way to push that group forward?
I particularly say that's a fantastic question only because we actually got the exact same question last year and I'm pretty sure the exact same question the year before. And so I'll be frank about this, right? There's lots of like nice ways to talk about it, right? But there's often a lot of ego involved in this, right? And a lot of social dynamic involved in this, right? We're talking about a change in process, about how a group operates. And so one thing I would recommend, right, is that going back to this idea of exposure, right, is showing them how things can get done in an improved way. And unfortunately, carrying that torch into a group can be really hard, right? I mean, because you are talking about, perhaps you are trying to change the social dynamic of a situation. And most of the time anyway, scientists are not the best at social dynamics and the healthiest about them, right? And I'll be completely frank about that. You see that, right? You see that in how some groups operate. But the other component is actually slowly building people, right? Depending on how resistant you think the group is, get somebody else, right? Work on somebody else if there's somebody you're writing code with most closely, right? Bring them on board, right? And sort of not quite the viral model, but the slow osmosis model, right, of bringing people through. But the other aspect of this is that most people hear software engineering and resist because their immediate thought is that what we're talking about is a huge, heavy process, or they're thinking that it means let's rewrite everything, or it will cost a lot. It demonstrates that it really doesn't have to be that, right? It doesn't have to be let's start today with an improved architectural model, or at least variable name models. Everything we're going to go through and change everything. Don't do that first. Start with the traditional one, although we've gotten past people resisting version control. Start talking about deploying the benefits of having some sort of version control capability, right? Not just in the spirit of controlling bugs and development problems, but also in the concept of provenance, right? Of really understanding what ran what simulation. But I would say go slow. I don't know if has anybody done this? Has anybody been part of a group and tried to bring in new practices successfully? Yeah, it is hard. We can talk about it more too, because I think there's also very specifics to a particular group about what people are willing to adopt. The other aspect to this is because the other aspect of this is if it doesn't necessarily work by sort of the viral model of slowly getting everybody one person at a time on your side. If it is very hierarchical in a group, right, and you have a PI who really sets that tone, sometimes it's sort of the matter of slowly working on them, and the process of funding, and that one often helps, right? When they see the fifth call in a row that says they need to have a software engineering practice, it's worth the conversation.
One of the reasons that projects are left behind and is being stranded is I worked on 2 or 3 different projects which are just left right now. So one of the reasons I think that happens is because we don't know in advance that whether this is going to complete the task that we have in mind. Is there any do you want to expand more on that? We start a project, and then when it is successful, then we want to incorporate all the software engineering practice so that other people can follow. And
I think that's a really great question, because it's true, right? If I'll paraphrase it and make sure I rephrase it right, is sometimes you just need to prove the concept. You just need to move forward and just prove a concept so you can actually, for example, get funding, right? You need to do that quickly. And so then once you have that code, how do you step backwards and sort of think about how you can bring software engineering to it? One answer I will give, which is if you, the developer, right, if you're the person, or you or 3 people, right, together are trying to get that done really quickly, there's this real base set of practices which are not onerous, which are not overwhelming, which you should consider, right, even if you are doing a proof of concept, right, because otherwise you'll get bit, right? So this concept of having version control, right, or having some shared basic coding standard, like basic ones, just so you guys, you can understand what you did 3 months later, or you and the group, right, can actually properly interact. Those are really important. So consider those. I'm sort of rejecting part of the premise, right? Consider some of these most basic ideas, even when you need to plow through. And understanding, right, that maybe if you have some of these basic, for example, coding standards, but you're trying to figure something out, you don't know if it's going to work in a routine or something like that, at least just flag it, right? You can document code, right? It's easy to throw comments in there, right? Think about ways that you can easily go back and identify areas that are not up to standard, or that are really just exploratory, or that are just a mess, right, and doing things that might not be good coding practices. Just make sure you have a way that you can find them. But really, don't plow into something without some of these basics. A substantial number of problems, right, I'm harping on the version control issue because I think many people get it today. A lot of people are using version control systems today because they've seen the benefit of it. So I use it as a good example that because many people have sort of seen the light of it. Without, for example, basic version control and basic testing, even when you're doing that prototyping, basic, simple testing, whatever you can cobble together, right, after the beer on Friday to get it done, whatever that basic testing is worth it to save that problem where you are under the gun, right? You are trying to prove a concept and you discover a huge problem 3 months later. And that throws you back and maybe knocks you out of contention, right, for whatever it is you're trying to do that with. But think through these, like these concepts of like basic documentation, even they're just flags to come back and look at this, right? And version control and some basic coding standards will help you be faster with that prototyping. And you might come up with your own, these are Katherine's like 10 things that she always does when she's writing a piece of code, right? And those are also valuable. If you just have them around that become your way of doing code that reflect some decent practices, it becomes even easier to incorporate that. So sort of a not answer. However, because I'm saying reject that and just do it anyway, but you can do it in a modest way. But the second is that there are a lot of code that have gone back and tried to introduce good software engineering practices afterwards. It's harder. It may be obvious, right? But it is trickier, right? When you want to go back and have, as I said, coding standards is just another good one, right? Like some common way of how you define or how you name variables and functions, right? So you can understand and read a code. It's a lot harder to go through and do a systematic change on that code. But it is possible. I will say with that is that there has to be a very well-defined process to do it, right? Define that process, set the testing up. Don't do anything like this without really good testing in your code. So that might be the first thing you deploy, depending on what the code has implemented in it, right? So think about unit testing and some sort of verification process within the code, and then start doing things like changing coding standards. Then start doing things like, walking through sort of whatever list you need. But make sure testing is in place. Make sure it's in place.